Modern physics. Modern physics failure of classical mechanics, ultraviolet catastrophe, photoelectric effect, Crompton effect, and Planck's hypothesis. The great success of classical mechanics, which includes the classical theory of electromagnetism, thermodynamics, made people believe that the ultimate description of nature had been achieved by the classical mechanics, and all non-physical phenomena could be explained within the framework of general theory of matter and radiation. But around the 20th century, the classical physics had been quite unable to explain some seriously challenged on two major fronts. First is relativistic domain, and second is microscopic domain. In 1905, Einstein theory of relativity shows that the validity of Newtonian mechanics cannot valid at very high speeds, which is the speed is comparable to that of light. As Newtonian mechanics stops cannot explain, cannot sustain at very high speeds. Another is microscopic domain. As soon as new experimental techniques is discovered to the point of probing atomic and subatomic structure, the classical physics fails miserably. And it is evident that the validity of classical physics cannot explain or cannot valid at the microscopic level, and that the new concept had to be invoked to describe for example, structure of atoms and molecules, and how light interacts with the matter, with the atom. So basically classical mechanics fails to explain both relativistic domain and microscopic domain. That's why the quantum mechanics required to explain the atomic and subatomic structure. The failure of classical physics to explain several microscopic phenomena such as blackbody radiation cannot explain by classical physics. Photoelectric effect cannot explain by classical physics. Atomic spectroscopy cannot explain by classical physics. Around 1900, Max Planck got real breakthrough. He introduced the concept of quantum of energy. In his efforts to explain the phenomena of blackbody radiation, he succeeded in reproducing the experimental results only after postulating that the energy exchange between the radiation and its surrounding takes place in discrete. It is quantized, not continuous. He argued the energy exchange between the EM waves of frequency nu, energy exchange between the EM waves of frequency nu and matter occurs only in integer multiplies of h nu, which is called the energy of quantum, where h is fundamental constant called Planck's constant. Blackbody radiation. We all familiar with the glow of a hot piece of metal, which gives off visible light whose color varies with the temperature of the metal. The color is changing from red to yellow and yellow to white as it becomes hotter and hotter. Other frequency also it includes which we cannot see with our eyes, but still its presence. Probably all objects radiate such energy continuously, whatever their temperature, through which the frequency predominate depends on the temperature. At room temperature, most of the radiation is in the infrared part of the spectrum, hence we cannot see, so it's invisible. The black body. The black body means the ability of the body to radiate is closely related to its ability to absorb the radiation. The black body is radiate 100% and is also radiate the it radiate 100% and also it absorbs also 100%, which we call the black body. It is expected since the body at constant temperature is in thermal equilibrium with its surrounding and must absorb the energy from them at the same rate as it is emits the energy. It is convenient to consider that it is ideal body, one that absorbs all radiation and emit all radiation. Such body is called black body. For example, in the laboratory, the black body can be approximated by hollow object with a very small hole leading to its interior. Any radiation striking the hole enters the cavity where it is trapped by reflection back and forth until it's absorbed. The cavity walls are constantly emitting and absorbing the radiation, and it is in property of this radiation which we called black body radiation. A black body radiates more when it is hot as compared to when it is cold. And the spectrum of hot black body has its peak at higher frequency. It is peak at higher frequency than the peak in the spectrum of cooler one. So here peak is higher frequency as compared to this one. So hotter one, the peak is higher frequency, cooler one, peak is lower frequency. The behavior of an iron bar as it is heated to progressively higher temperature. First it glows dull red, then it's going to bright orange red, and eventually it becomes white hot. The spectrum of blackbody radiation is shown in figure with two temperatures. This is the spectrum of blackbody radiation. Here is the frequency and here is the spectral energy density U nu d nu. as the frequency increases, the energy density increases. It's going to be highest as its peak, and then it reduces as increases the frequency. So that is the spectrum of the blackbody radiation. Next one is ultraviolet catastrophe.